This video is about the methodology at the heart of machine learning and why it's generally misunderstood even by some of its greatest champions. Here's the basic setup. We imagine that we're given a data set, and the data set is made up of inputs, call them x1 up to xn, and labels, call them y1 up to yn. Our job is to learn a function that predicts the label given the input. For example, we can do it with a neural network. For what I'm going to say here, it doesn't matter at all what sort of neural network we're talking about, how many layers and how many neurons and so on. What matters is simply that it's a black box function that takes an input and produces an output. It might as well be a box full of grumpy parrots inside. Typically, though, it's a neural network and it has millions of parameters that can be tuned, and by tuning them, we'll be able to make our function f fit the dataset. But we don't want our neural network to cheat by just memorizing the data we give it and, well, parroting it back to us. So we split our dataset into two parts. One part, the training data, we use to train the neural network, i.e. to fit the theta parameters. The other part, the holdout data, we set aside, and once we've finished training, we measure how well our trained neural network does on this holdout data. Let's put this down more formally. The whole setup is called Supervised Learning. We have data consisting of x-y pairs where y is called the label, and we want to learn to predict the label. We invent a black box function to do this, a parameterized function, and we tune the function parameters to try to make good predictions. Then we measure how accurate our predictions were on the holdout dataset, which we weren't allowed to look at all while training. To talk about prediction accuracy, of course, we have to have a way to measure it. For this sort of problem, where we're trying to predict a numerical label, we might as well use an evaluation metric, something like this. Just look at the predictions our trained neural network makes. I've written theta hat here to emphasize the trained theta parameters, and measure the mean square error when compared to the ground truth labels, the labels in the dataset. If our task was classification, in other words, if the y's were discrete, then we could instead use a loss function that measures whether or not our predicted label was correct. Whatever the problem, you just have to choose a loss function that's appropriate for the type of predictions you're trying to make. Nothing I've said so far is specific to neural networks. As I said, my black box predictor function might as well be a box of angry parrots. But if the function is nice and simple, then there's an obvious way to train it. We know that in the end, we want to get a good score when we measure prediction accuracy on the holdout dataset. So let's pick theta to get good prediction accuracy on the training dataset. This is what I mean. By the way, when I write argmin, it just means that I'm interested in the theta that minimizes the loss. I don't care about the value of the loss per se, only about the theta where it's optimized. Arg is short for argument, and so you should think of this as some sort of loss function that takes theta as an argument, and we're looking for the value of the argument that achieves the minimum. The nice thing about this method of training, and what makes neural networks practical, is that there's a pretty good way to do this optimization numerically. It's called gradient descent, and all it needs is for f to be differentiable with respect to theta. Neural networks are made up out of such simple building blocks that the function f is trivial to differentiate. Although there is actually a snag when the labels are discrete, in other words when we're trying to train a classifier. I said that we need f to be differentiable with respect to theta, but what I should have said is that we need the loss function to be differentiable, because that's what we're trying to minimize. If we define the obvious loss function for a classifier, i.e. just a count of how many we got wrong, then that's not a differentiable function of theta, and so you can come up with hacks to make the training objective be differentiable. The hack is called cross-entropy softmax. Let's set that aside for now though. Here's an extract from a thoughtful piece about machine learning versus statistics by an ex-statistician called Leo Breiman. Have a read. Here are two phrases that catch my eye. In the mid-1980s, a new research community using neural networks sprang up. Their goal was predictive accuracy and complex prediction problems where it was obvious that data models were not applicable. By this he means We're not even trying to build models of the sort that we've studied throughout this course. It's just a free-for-all of black boxes, and whoever's black box makes the best predictions, they win the prize. But there's a problem with this way of thinking. Here's another type of machine learning called unsupervised or generative learning. Let's suppose we're given a dataset, for example, a dataset consisting of photos of faces, and what we want to learn is how we can synthesize new faces. Or maybe we want to learn about clusters in the dataset, for example, to automatically group them without any supervision. Wouldn't it be nice if the machine could, for example, learn to distinguish young and old or happy and sad without having to be told any explicit labels? But the question here is, how on earth should we evaluate such a machine? Is there any sense at all in which we could keep back some holdout data and test our machine's performance on that holdout data? What would we be comparing it to? You could imagine some sort of human-in-the-loop evaluation system. Take some machine-generated faces and ask the human to evaluate them. Or better, take some machine-generated faces and some holdout faces from our data and ask the human which one looks more genuine and hope that the human can't tell. If so, then our machine has done a good job at synthesizing new faces. But this is pretty useless. It doesn't scale. It's not really machine learning if we need human input every step of the way. I think everyone would agree that this is a useful thing to be able to do with machines, and most people would agree that it deserves the title of machine learning, but it doesn't fit into Breiman's language of predictive accuracy. This is the point where probability theory rides in to the rescue. We need to stop thinking about predictions and accuracy, and we need to start thinking about probability modelling. Here's how a probabilistic modeler sees the problem. We're given the labelled dataset as usual, xi the predictor variable for record I and yi the label, and we'll invent a probability model for the labels. Let's call our generic label random variable big Y and write our likelihood function as PR sub big Y of little y, parameterized by the predictor xi and the unknown parameters theta. The training goal, the idea we started with right at the very beginning of this course, is simply maximum likelihood estimation. In other words, pick the parameters to maximize the likelihood of the observed data. Let's just write out an example, one that we've looked at so many times already. Suppose our probability model is that the labels are normally distributed with mean f sub theta of xi and variance sigma squared. Here f could be anything at all, but I'm thinking of f as a neural network and theta as the edge weights. The training goal is just maximize the likelihood of the dataset, or let's say maximize the log likelihood of the dataset. And as we've seen many times already, we end up with this very simple expression. And this is exactly the same loss function that the prediction accuracy crowd would use. So the big message is this: training a neural network is fitting a probability model, and it's fitting in the most basic way that we can possibly think of, namely maximum likelihood estimation. And what's more, the obvious loss function for a neural network with labels that are real numbers is the mean square error, and that corresponds to the most basic probability model we can think of, namely the normal distribution. It's just like the linear models we spent so much time on, just with a richer predictive function. One thing to note, you may look at this probabilistic modelling exercise and think, hey, it's totally arbitrary. How do I know what probability model to use? But the prediction accuracy crowd also have a totally arbitrary choice, namely what loss function to use. There's nothing much in it whether you as the modeler have to invent a probability model or you as the machine learning expert have to invent a loss function. In fact, this is exactly what Gauss's genius insight was, that normally distributed errors and quadratic loss functions are basically the same thing. Now, you might look at this with a skeptical eye and think to yourself, okay, well that's interesting, but it hasn't actually told me anything new. It doesn't give me any better predictions, it's just fancy clothes for the same method. That's not quite true for two reasons. First, a little reason. In this model that we just looked at, I assume that the noise parameter sigma was known, but there's no reason why it can't be treated as just another unknown parameter and optimized along with the rest of theta. And in fact, we don't even have to limit ourselves to a constant sigma. We could allow it to be a function of the predictor variable also. When you see the problem as a probabilistic modeling problem, It opens your eyes to all sorts of extra models that you could fit. But there's a much bigger reason why probabilistic learning is better. Unsupervised learning. If we set up the unsupervised learning task as simply find the probability model that describes my dataset, then it's obvious how we should train it. We train it exactly how we train the supervised learner. It's just maximum likelihood estimation. So that's the other big takeaway. Probabilistic modeling is the best way to think of machine learning because it makes it totally obvious how to make sense of unsupervised learning. Let's go back to Leo Breiman. I don't like this idea that the goal is predictive accuracy. It's too restrictive because it doesn't let us talk about unsupervised learning. And I'd also take issue with his claim that data models are not applicable. The standard machine learning training method corresponds precisely to a probability model for the data, and what's more is the simplest possible probability model, one invented over 200 years ago by Gauss. But I haven't yet talked about the real cornerstone of machine learning, the idea of holdout datasets. Here's another quote by Noam Chomsky. There's a notion of success which has developed in recent years which I think is novel in the history of science. It interprets success as approximating unanalyzed data. He expresses himself carefully, by the way. He says success is approximating unanalyzed data, which is carefully phrased to apply both to supervised and unsupervised learning. That's what you get with geniuses, razor-sharp precision. You read what they say, you go away and think up some objection, you come back and reread it, and you discover that they anticipated your objection and you were too slow to realize it on your first reading. So let's talk about holdout datasets, Chomsky's unanalyzed data, and how it fits in with probability modeling. Here's a dataset. I'm going to think of this as an unsupervised learning task. In other words, my data set consists of points in R squared, i.e. each data point is a pair of numbers, and I want to fit a probability model. We might go through several models before we find one that we're happy with. We might start out by modelling the pair xi as two independent random normal variables, each with their own mean and variance. If I plot the joint density, it would look something like this, high around the means mu1 and mu2, tailing off further away. This model will give a fairly low value for the likelihood of the entire dataset because all of the points are on the periphery where the likelihood function is low. Remember, this is a joint density that I'm plotting here, so it has to integrate to 1. So putting lots of probability mass right in the middle means that there's very little to go round at the edges. So we try something cleverer. We look up on Wikipedia and we learn about multivariate normals, i.e. correlated normal random variables, and we fit the parameters so that we put more probability mass in areas of the plot where there are lots of data points. This will increase the likelihood of the entire dataset. And so we get cleverer, and we invent some wacky and wonderful function with lots of parameters, probably using a neural network, and this function puts lots of probability mass in areas where there are data points and very little elsewhere. And so according to this probability model, the likelihood of the entire dataset is high. And then a big brain person comes along and tells us, you should use the empirical distribution of the dataset as your model. It's a probability model that puts probability mass exactly where the data points are and nowhere else. And so it makes the likelihood of the dataset very high as it can possibly be, because it doesn't waste any of its probability mass by smearing it around in regions with no data points. Okay, so the empirical distribution is a perfect fit to the data. But it's a rubbish model. It's rubbish because it's no good at generalizing. Remember, we've set this up as an unsupervised learning problem. What we're after is a probability model that we can use to synthesize new data points. The joint likelihood function in the middle plot assigns positive likelihood to all sorts of regions in the sample space, which means that the random variable might reasonably well take values in those parts of the space. The empirical distribution, on the other hand, assigns all those regions a likelihood of 0, which means that it's doomed to just regurgitate the data points in the dataset that it was given. To evaluate how good we are at generalizing, i.e. how good our model is at synthesizing novel data, we can use holdout data. Let's imagine we've kept a holdout data point aside, and now let's measure the likelihood of that holdout data point. The fancy parametric model in the middle plot gives it a reasonably large likelihood, and the empirical distribution gives it likelihood 0. So let's summarize. In unsupervised learning, our high-level goal is to be able to synthesize new data points. We can train a model by maximizing the likelihood of the training set, but we shouldn't get carried away. We can then evaluate how good our model is at synthesizing novel values just by keeping a holdout dataset and measuring the log likelihood of our model on the holdout data. I should also mention supervised learning here. Here's the setup. Of course, we'll use the same evaluation metric, the log likelihood of our fitted model on holdout data. I won't talk through all this in detail, but it's not hard to see that getting a good likelihood on holdout data is the same thing as making accurate predictions. So this is the real big deal of probabilistic modelling. If we think in terms of probability modelling, we have a nice, clean, easy, principled way to think about model evaluation, and it's just as good for supervised as for unsupervised learning. If we don't think probabilistically, it's hard to even know how to start thinking about how we should be evaluating an unsupervised learning system. Let's turn back to Chomsky. Chomsky talks about a notion of success which I think is novel in the history of science. He doesn't mean novel as in new and exciting and groundbreaking. It means novel as in new and misguided, a travesty of what science should be. Here's a picture to explain what he means. This is the machine learning mindset. The machine learning idea is that the job of a model is to generalize to new data, and we can make sense of that both for supervised and unsupervised learning, as long as we think probabilistically. It's easy to test how well our model generalizes using holdout sets and measuring our model's log likelihood on those holdout data points. Typically, a machine learning person might shuffle their data and take 20% at random to be the holdout data set. Chomsky would say that this is deeply misguided. Here's a scientist's way of looking at the world. The scientist wants to learn how the world works. They want to come up with theories that will work well in completely new scenarios, well beyond the data set that they use to invent the theory. Einstein's theory of relativity, for example, continues to be tested after his death, using instruments and data well beyond what he knew about. A scientist would say that if your model only works on a random subset of your initial data, then it's a rubbish model. And so, generally speaking, they don't trust machine learning. They trust simple models based on understandable parameters, based on well-grounded scientific concepts, because they trust that that sort of model will extrapolate well to completely new situations. Here's what Einstein had to say about simple models. Everything should be made as simple as possible, but not simpler. Actually, that's not what Einstein said. What he said is rather less simple. Now, I don't think it makes sense to be absolutist about this. We shouldn't expect our theories to apply to completely and utterly new scenarios that have nothing at all in common with our experience. It's reasonable to want our models to apply to reasonably new data, but not completely off-the-wall new. So what I'd recommend, to just get a little bit closer to the scientist mindset, is that you don't do the usual machine learning thing of taking a random subset of your data to be holdout. Try to find a holdout set that's different to your training set. For example, take the most extreme 20% of your points, if you can find some way to measure extreme. That's the best way to make sure you're actually learning models that can generalize. Now, we've talked about three types of model. There's the machine learner's model, which fits the training data reasonably well and can generalize within the confines of the holdout data. There's the scientist model, which values simplicity and hopes to generalize well to completely new scenarios. And we also saw the other extreme, the empirical model, which fits the training data perfectly but is completely rubbish at generalizing. You may have gotten the impression that empirical distributions are the sort of idea that looks great at first but then falls apart when you look deeper. Let me try to persuade you otherwise. What we've decided as machine learners is that we should be evaluating our model by the log likelihood of the holdout dataset. But we don't care about the holdout dataset because each one of those points in it is special and precious to us. No, we only care about it because we think it's representative of the whole great big world of unseen data. In other words, what we're doing is we're approximating the whole world of unseen data by a sample from it. In other words, we are using the empirical distribution. This is the real heart of machine learning. It's not model fitting and it's not neural networks. Model fitting is an ancient technique. Gauss did it back in the early 1800s, and neural networks are just slightly fancier model functions. No, what's new and groundbreaking about the way we do machine learning now is the idea of evaluation on holdout datasets. And the fundamental idea of a holdout dataset is that a finite sample of data points is a suitable stand-in for the world of unseen data. In other words, the heart of machine learning is the idea of the empirical distribution.